Hi guys, Harry here. Welcome to Scrap Science. From looking at the title of the video, you can probably tell what we're going to be doing today. So right from the start, it's a good idea to not work on the bench. We're going to be moving outside. It has been a whole 3 videos on Scrap Science where we haven't done any electrochemistry whatsoever. So before I go mad, I have a pretty big one, a pretty good idea I think that a lot of people will enjoy. And that is making sodium metal. I've been getting requests to make sodium for I think years now, so finally we're going to get around to actually doing it. The process that we're going to be using to make our sodium metal is probably the most common way for people to make sodium at home, and that is the electrolysis of sodium hydroxide to give us sodium metal. This is some sodium hydroxide that I got from the local hardware store. It's very available where I live. I think I can even get hold of it in most supermarkets as a cleaning chemical, but for the cases where it's not readily available, I have made quite a few videos in the past about how to make this stuff from sodium chloride. Now the process for turning this into sodium metal is actually relatively simple, at least if we compare it to other molten salt electrolysis procedures, because the only 2 steps involved in converting this into sodium is to first melt it and then apply direct current to it in order to electrolyze it, and on the cathode we will generate sodium metal. There are some intricacies to the procedure, but we will get to that a little bit later. This procedure is actually how sodium as an element was first isolated back in 1807 by Sir Humphrey Davy. He performed the experiment in pretty much exactly the same way that we're going to be doing it today. Maybe he used some slightly different electrodes and a slightly different crucible to hold the molten sodium hydroxide, but overall the procedures are incredibly similar. Similarly, this process was patented in 1888 by Hamilton Castner, who then went on to develop the process and use it as the main industrial route for making sodium right from 1888 up until around 1926, when a better process was developed for making sodium metal. So that's why the process that we're doing today is called the Castner process. Anyway, as I said before, the first step of this process is to melt our sodium hydroxide, and that's easily the most involved part of this process because molten sodium hydroxide is really not nice to work with. The melting point isn't too bad, I don't think. I think it's around 320 degrees Celsius, but the molten mass is just so chemically aggressive that it really needs a pretty good safety mindset and a relatively inert container to do it in. Graphite crucibles are usually going to be best here, although some types of ceramic I believe work. I'm going to be using stainless steel as the container to do our electrolysis today. Stainless steel is relatively good with the molten sodium hydroxide. I just went out and bought a few stainless steel measuring cups, and I think this one will be a good size. Once we've got the salt in the molten state, all we need to do is pass some DC current through it and electrolyze it. On the positive electrode, the anode, oxidation occurs, so we steal electrons from the hydroxide ions, and that results in the generation of water and oxygen gas. On the cathode, reduction occurs. This is the negative electrode. Electrons are given to sodium ions to form sodium metal. There's actually quite a selection of electrodes which are inert enough for this process to work. What I'm going to be using today are just some graphite electrodes, but nickel apparently will also work well, and even iron will work to some degree for quite a long time. Other common metals, even stainless steel, will dissolve into the molten sodium hydroxide, at least to some degree, as the electrolysis proceeds. And that's the basic idea of it. Once we've got the cell together, the Castner cell, we can make sodium with relative ease. And the temperature of the cell isn't even so high that we require an inert atmosphere to protect the sodium. Just doing it under atmosphere tends to be fine. In fact, this procedure is popular enough in home chemistry that if you look on YouTube, you'll probably find a whole bunch of people who have built very professional, in my opinion, Castner cells for efficient and very high production rate generation of sodium metal. As good as it is, there are drawbacks to using a Castner cell to make sodium, and these drawbacks are pretty serious in my opinion, to the point where I would go so far as to say that the Castner process is just bad. I don't like it very much. The first drawback of this process is the fact that we're working with molten sodium hydroxide. I said this before, it's really not nice to work with, and if you get some on your skin, it has a tendency to just dissolve flesh. So, it's nothing we can't work with outright for being toxic or something, but it does require a great deal of care when we're doing this. The real struggles of this process begin due to the fact that we need extremely precise temperature control for the Castner process. We need to melt the sodium hydroxide at around 323 degrees Celsius, but if we go too much higher than that, say 340 degrees Celsius, not all that much higher, sodium becomes slightly soluble in the sodium hydroxide melt. So as we're generating the sodium on the cathode, it will just dissolve back into the melt and we won't be able to recover any product. So it completely ruins the process if we run it slightly too hot. Even if we have good temperature control and we're able to stop the sodium from dissolving into the melt, the worst bit is that the anode reaction generates oxygen and water. Now the water is the biggest problem. You'd think that at 330 degrees Celsius, the water would just boil off, but even at those temperatures, the water will kind of dissolve into the sodium hydroxide to some degree, and then water is a lot easier to electrolyze than sodium hydroxide, so it subtracts from our yield of sodium by, instead of electrolyzing our sodium hydroxide, we end up electrolyzing water to generate oxygen and hydrogen instead. This problem also gets worse if you try to increase the production rate or run the cell for a long time. To solve this problem, you can't just crank up the heat on the cell to boil all the water off because of the sodium dissolution problem I talked about earlier. What you actually have to do is run the cell for a short period of time, extract your sodium, turn off the cell, and then heat it up to get rid of the water, and then cool it back down before restarting electrolysis. And you've got to do this over and over again in order to get multiple gram quantities of sodium over a long period of time. These aren't really big problems when we're working on such a small scale as we're going to be doing today in just a cell like this, especially if we're not going to be running it for longer than an hour. But for well-built cells, where you want to be generating hundreds of grams of sodium total, these problems are real issues and it takes quite a bit of engineering to get around them. From a bit of research I did, I was only able to find a couple of people online who have reported that they were able to make more than 100 grams of sodium by this method, so it is really quite a difficult thing to do on a large scale. Nonetheless, we're going to try it today on a small scale because despite the fact that I think it's a bad process, it is a relatively easy one and it is a very interesting one. In the future, I have plans to build a Downs cell, which in my opinion is a much better electrolytic technique for generating sodium metal, involving sodium chloride instead of sodium hydroxide, but that is quite considerably more difficult and it'll be a while before I actually get around to trying that. But anyway, we're ready to go, so let's get everything set up. And here is the cell. As you can see, there's not much to it. I've just got our sodium hydroxide in our stainless steel measuring cup sitting in the furnace, slowly heating up. So I'll get this to the point where it's just melting, and then we will turn on the current between our two graphite electrodes. So nothing else to say. I'll get back to you when it starts melting. All right, we are finally all the way melted and it's just finished melting, so I think we might just be in the right temperature range. I've turned the furnace off so that we can stay at around this temperature, and I'm about to turn on the electrolysis. So watch the cell. Oh yeah, that's what we want to see. Right, as it turns out, this isn't really working at all. The graphite electrodes I'm using seem to be falling apart in the molten sodium hydroxide mixture. This isn't the worst thing, it just means we're going to have to try this again. I'm thinking instead of using graphite electrodes, which I really did think would work, we would just use some strips of nickel, which we know will work because other people have done it before. All right, trying once again. This time we're using nickel as the cathode because oddly enough, I wasn't expecting this, but the cathode was actually the electrode that was falling apart last time and causing the cell to not work. So we're keeping our graphite anode and swapping out our cathode for nickel. Hopefully that'll work, but if not, we can always swap out our graphite anode for another nickel electrode as well. Anyway, what I'm doing right now is preheating the stainless steel crucible, just so that we don't have to have sodium hydroxide sitting in there, absorbing water from the air as we're heating it up. Alright, commencing electrolysis once again at 5 volts, gives us instantly around 5 amps. And as you can see, initially we get a lot of bubbles on both electrodes because every sample of sodium hydroxide that you can get commercially is going to have some degree of water in it. So that's what's going to be electrolyzed first. We're going to electrolyze water into oxygen and hydrogen before we can get to our sodium. I see sodium. I don't want to put the camera too close from the fear of it getting sprayed with molten sodium hydroxide, but just if we zoom in, digital zoom I know, but just on the very edge of that cathode on the right, you can see a bead of sodium metal. Very nice. So if we leave this going for maybe, I'm hoping to leave this going for an hour maybe, in total, hopefully we will amass quite a bit of sodium. Alright, you can see a couple of big globs of sodium forming right now. It's been about 10 minutes. Before we get ahead of ourselves, I'm going to try to extract the sodium that we've made so far, just so that we've got some yield before anything goes wrong. So I'm going to turn off the cell and then just scoop out the sodium with a little stainless scooper. To store the sodium, just as I take it out of the cell, you can see I've just got a beaker full of mineral oil, and we're storing it under that because that's the only way to properly protect it from the air and the atmosphere. I need to get better at scooping it out because you can only see that 1 second from the left is sodium, but the rest of them are mostly sodium hydroxide. So maybe I'll get better at that as we take more sodium out of the cell. Alright, an hour and a half on, I think we've got about all we can get out of this cell. We have run into the problem that we're just not getting much yield at this stage, and the sodium hydroxide is quickly freezing over. Over the 90 minutes that we've had the cell running for, we have quite a yield amassed in our beaker full of sodium. I'll show you that later. I can't show you that with these gloves on very well, but I'm going to shut down the cell and then we'll try to purify our sodium. Here we are. I have shut down the cell and disassembled everything, and this is what we're left with. If we start out having a look at our nickel cathode, you'll notice that really nothing at all has happened to that. It has done its job perfectly. It's still covered in a little bit of sodium hydroxide, but that hasn't degraded at all really, which is to be expected. It is nickel and it is being used as a cathode. Our anode, our graphite anode, did get eroded ever so slightly. If we get that to focus properly. Hello. Yep. A little bit of the graphite did fall off the end of our electrode there, but that's nothing to worry about. Maybe the cell would have done a better job if we had have used nickel as an anode as well, which apparently is also an option, as I said before, but we went with this anyway and it worked fine. Our cell is looking a lot better than I expected, actually. The oxidation that it received from being used as the crucible for our electrolysis is pretty much just a surface coating and could easily be rubbed off just with a wire brush, I think, and make this measuring cup look as good as new. It still has a little bit of sodium hydroxide in there because despite the fact that I left this in a beaker full of water overnight to get rid of the sodium hydroxide, it turns out, surprisingly, that solid masses of sodium hydroxide take quite a while to dissolve in water. So, you know, this still hasn't dissolved away, but it'll get there and we'll have our stainless steel measuring cup as good as new after that is finished. Maybe I'll go on to use this for other molten electrolysis experiments, but for now I am impressed with how well it held up. And finally, we have our yield, which, you know, we didn't extract much sodium. There's only a few, maybe milliliters worth of sodium that we were able to get out. I'm not sure what that is in mass, but we'll find out later. And a lot of it is heavily contaminated with sodium hydroxide at this stage, but, you know, we did actually get more sodium than I thought we'd get. I'm pleasantly surprised. And, you know, despite what I said about the Castner process being annoying and bad, it is actually quite convenient for generating small quantities of sodium. Although, you know, I will restate once again that generating large quantities of sodium like this will require a much better cell. Anyway, the last step I want to do is just coalesce all of these sodium beads into one big chunk, and then I think we'll be done. To get the sodium all in one piece, it's relatively easy. The melting point of sodium is about 100 degrees, a little bit under, so we can just heat up our mineral oil. As you can see, that's making the sodium slightly react with something in our oil, but that's okay. And eventually our sodium will melt, and hopefully it'll be relatively easy to push them all together. Well, yes, this stage of the process took ages to get all of the sodium to coalesce, but I believe I've done it as well as I can. This is all of the sodium hydroxide and whatever else was on the sodium. There's a tiny little bit of sodium left in there, but, you know, that should be as much as I can do. And we have finally got it all together. There's also some tiny little droplets around the edges of this beaker too, but we have our big bead of sodium, which is going to represent our final yield. And yeah, here we are, 540 milligrams of sodium. This is, in the end, you can see it is nice and shiny when it isn't oxidized. I'm not sure what kind of percentage yield we got, based on the fact that we were probably running 5 amps through the cell for about an hour total. I don't know, editing Harry can figure that out in a sec. Anyway, to finish off, what I'm going to do now is get that out of there, and what I want to do is slice off a small section of it. This is relatively easy because sodium is such a soft metal. Get you a good look at that shiny surface underneath. Oh, it's quickly oxidizing. I'm going to store this piece of sodium in a little vial like that. You can see it slowly reacting with whatever is in the mineral oil, but that quickly stops after a little while. I'll save this as just a sample of the sodium that we made today. And then with this final little piece, I'm just going to chuck it in some water because I know everyone wants to see that. Here we go, ready? Well, that was slightly disappointing. Didn't even catch fire, but You know, I don't really want to waste my sodium on doing that again. So I suppose you'll just have to look elsewhere if you want to see like a full-scale reaction where sodium explodes or catches fire on contact with water. But you know, that is at least absolute confirmation that we do have sodium. That is the classic sodium reaction with water. So there we have it. That's the Castner process. We were able to melt sodium hydroxide, electrolyze it, and produce sodium metal on the cathode. And we were able to get this relatively sizable chunk of sodium out of it in the end. So I'm very happy with what we've done today, and I hope you enjoyed it as much as I did. And if you did enjoy this video, I would definitely recommend checking out one of my other videos about making aluminium metal, seeing as it also involves some high temperature electrolysis. But with that, until next time we try some molten salt electrolysis, I'll see you later.